tape's rolling.
Okay, this is our setup. It's pretty much just the Hot Wheels ramp. Set up with a piece of wood, taped together. It takes pretty efficient. We nailed the track down to keep it steady so we get constant results. And basically what we did is we take this cart, we put it at the top and we launch it, try and land it in the bucket. Using kinetic energy as one of our things, we found that this point right here would be the point where the velocity would equal the velocity there because it didn't go off the track, so 0 here, 0 there. So we knew that if we could find the velocity right here, that we could find the velocity here at the launch point and then use projectile equations to figure out how far it would land. So what we did was we took the distance, we used the Pythagorean theorem, and we found the distance from here to the top where we marked, and then from here to there, and we found this length. And as we had this length, we also used inverse tan to find the angle of this
triangle.
Yeah, this triangle. And when you take that, when you use the sine of the angle times by 9.8, which is the acceleration of gravity, you can find the acceleration down this incline. I mean, there of course there's force of friction and stuff like that, but since we're using a cart on wheels, we hope it's not that much. And so we found, using calculations, we found that the velocity here coming down would be around 4.9 meters per second, so we figured this would be around 4.9 meters per second. Then we used actually to do this, we used the no time equation, if that's important to you. And then once we found the velocity here, we then took the height above the ground, and then we found the x and y velocities and then just determined how much time it'd take for the cart to leave here, go up, and hit the ground. And once we knew how long that took, we could use the x velocity to determine how far it'd go over in that time. So if I could get one of y'all to get a bucket and put it 1.8 meters from the stand.
She's the bucket.
Okay. And actually make sure that she like lines it up with the ramp. And I'm gonna. Is it lined up? Yeah. We're gonna put the cart up here on this line that we have drawn.
Oh.
And
Not yet, not yet, not yet.
and
Close enough for all that.
away it goes. Oh! Too far.
Give him a hand.
Okay, this was trial number 2, and we looked back at our numbers, and we decided as a team that we may have eyeballed our measurements a little too much, and that we may have undershot a lot of our numbers and took off numbers, making the,
Rounding too soon.
Yeah, rounding down, and our numbers came up short, so we went over it again, we looked it up, and we also are going to use a taller bucket this time, so we moved it back 8 centimeters, and not 8, but 10.
Hey.
Yeah. We're gonna put it right next to it. And now, if this doesn't work, I'm gonna quit.
You move it over like that. Okay.
Now
we pray.
Now we pray.
Oh!
I told you that. We've determined that through our extensive trial runs that the wheels in the car have gotten looser now, so the car's actually going further than it's supposed to. So we're going to try it again. We moved the bucket back a couple more centimeters. We're going to try and make it this time, so we prayed the last 2, now we're not going to pray. Here it goes.
This person got us in.
Oh! The wheel's off the track, the wheel's off the track, we get a redo.
Okay, go ahead, do it again.
This proves Murphy's Law.
He adds a little comedy. Here we go.
We should go back like we're not graduating.
Third time.
All right, quiet.
God be with you, little car. Oh!
God's time.
We're gonna move the bucket back forward.
Because our car is down. You need a bigger bucket.
We realize gravity's not reliable, so
Just a theory.
it's not as constant as they say it is. Yay! In the foul!
All right.